This video is the first of two videos in which we'll learn about integers. In this video, we'll focus on representing, adding, and subtracting integers. The second video will address multiplying and dividing integers. Integers can be used when solving problems, such as determining differences in time zones. Let's begin by exploring two common representations of integers. In earlier grades, your child placed and spaced whole numbers on number lines. Here, 6 is placed 6 units to the right of 0. In grade 7, your child is formally introduced to numbers less than 0. These numbers can be placed and spaced on number lines that extend to the left of 0. For example, -6 is placed here, 6 units to the left of 0. These signed whole numbers less than 0 make up the negative integers. Notice that as the numbers get smaller, their distances from 0 increases. That is, -6 is less than -5, despite 6 being greater than 5. It's further from 0. The positive integers are whole numbers greater than 0. We can attach a positive sign to each of these integers to highlight this. Together, the positive integers, the negative integers, and 0 make up all of the integers. 0 is neither positive nor negative. Pairs of integers that are at equal distances from 0, like positive and -6, are called opposite integers. Opposite integers will become very important when we explore adding and subtracting integers. I chose to represent the integers using a horizontal number line. A vertical number line works too. In fact, you may be more familiar with this representation. In addition to number lines, a second representation of integers, two-color counters, can be helpful. One yellow counter represents +1. One red counter represents -1. Think of these counters as physical stand-ins for points or penalties, credits or debits. Combining +1 and -1 makes 0. Together, one yellow and one red counter is called a zero pair. 0 can take on different representations. For example, 2 yellow and red counters, or 3, or even 6. Now that we have two ways of visualizing integers, we're ready to investigate adding them. Take a moment to consider this collection of counters. What equation does it represent? Five red counters have been joined with 3 yellow counters. Remember that red is negative and yellow is positive. Therefore, this image represents -5 plus +3. To determine the sum, we make use of zero pairs. Notice that the 3 yellow counters can be matched to 3 of the red counters. Because each of these pairs make 0, they do not contribute to the sum and can be removed from the pile. I'll show this by fading these colors, just so we can keep track of how we arrived at a sum. Tossing out the 3 zero pairs leaves 2 red counters, or -2. What happens when we play with the signs of the numbers? +5 plus +3 can be modeled by joining 5 yellow counters with 3 yellow counters. The result is 8 yellow counters, or +8. This isn't surprising. After all, we already know that 5 plus 3 is 8 from our understanding of adding whole numbers. Similarly, -5 plus -3 can be modeled by joining 5 red counters with 3 red counters. This time, the result is 8 red counters, or -8. Only the color has changed from the previous equation. Joining 5 yellow counters with 3 red counters portrays +5 plus -3. Once more, we can look for and remove zero pairs. Doing so leaves 2 yellow counters, or positive 2. How can we use number lines to reason to these results? We'll explore this question next, beginning with positive 5 plus positive 3 is positive 8. First, we locate positive 5 by moving 5 units to the right of 0. Next, we slide a further 3 units to the right, landing on positive 8. What about negative 5 plus negative 3? This time we locate the first addend, negative 5, by moving to the left of 0. The second addend, negative 3, tells us to slide a further 3 units to the left, arriving at the sum negative 8. What about adding opposite signs, like positive 5 plus negative 3? Again, move to, or start at, the first addend. Here, 5 units to the right, because 5 is positive. From this position on the number line, slide 3 units to the left, because 3 is negative. This places us at positive 2. The sum is positive because we move further to the right than to the left. Continuing to play with the signs, the last sum is negative 5 plus positive 3 equals negative 2. Moving 5 spaces to the left, then 3 spaces to the right, places us 2 spaces to the left of 0. The sum is negative 2 because we move 2 more spaces to the left than to the right. Let's try our hand at subtraction. We'll start with what we know, subtracting positive integers. One way to think about subtracting is as removing or taking away. Subtracting positive 3 from positive 5 can be modeled by removing 3 from 5 yellow counters. I'll use arrows to show taking away. This leaves 2 yellow counters, or positive 2. Subtracting negative 3 from negative 5 can be modeled in a similar way. The only change is the color of the counters. This time we begin with 5 red counters, then take 3 away. This leaves 2 red counters, or negative 2. What about positive 5 minus negative 3? This presents a challenge. How do we remove 3 red counters from a collection of all yellow counters? How do we take away what isn't there? A creative solution lies in 0 pairs. Adding 0 does not change the value represented by the pile of counters. This still represents positive 5, as does this and this. Adding 3 0 pairs sets us up to perform the subtraction. Removing 3 red, or negative, counters leaves 8 yellow, or positive counters. Subtracting negative 3 from positive 5 can be modeled in a similar way. Add 3 0 pairs so that we have enough positive yellow counters to take away. Negative 5 minus positive 3 is negative 8. Next, we'll make some connections between adding and subtracting integers. The 4 subtraction equations that we just explored are presented up top. The 4 addition equations from earlier appear below. How are adding and subtracting integers related? You might have noticed some similarities between these vertical pairs of equations. Subtracting negative 3 is equivalent to adding positive 3. And subtracting positive 3 is equivalent to adding negative 3. In general, subtracting an integer is equivalent to adding its opposite integer. Why? To reason why, let's analyze the first two pairs of equations. In the first pair of equations, we begin with positive 5 yellow counters. Above, we add 3 zero pairs so that 3 negative red counters can be removed. The net result of these actions is 3 more positive yellow counters, as is true of adding positive 3 below. In the second pair of equations, we begin with 5 negative red counters. Above, we take away 3 negative red counters. Below, we add 3 positive yellow counters, which are paired with 3 negative red counters. Discarding 3 zero pairs has the same effect as removing 3 negative counters. 3 fewer red counters. A second way to think about subtraction is as comparing or finding the difference. Let's briefly explore this idea. Positive 5 minus positive 3 asks, how far is 5 from 3? 5 is 2 units to the right of 3. The difference is positive 2. Negative 5 minus positive 3 asks, how far is negative 5 from positive 3? Negative 5 is 8 units to the left of positive 3. The difference is negative 8. Let's apply our understanding of integers to solve the next set of problems. Over 3 days, the value of a stock fell 7 points, then went up 8 points, then fell 3 points. Decreases in value can be represented using negative integers. Increases in value can be represented using positive integers. What was the overall change in the value of the stock? The overall change is the sum of the daily changes. We can add these changes from left to right. Negative 7 plus positive 8 can be modeled by joining 7 red counters with 8 black counters. Discarding zero pairs leaves positive 1, an increase in the value of the stock over the 2 days. Making sense of the context itself can also help us reason to this result. The magnitude of the rise on the second day exceeds that of the fall on the first day by 1 point. This change is represented using a positive integer. Adding negative 3 can be modeled by adding 3 negative red counters. Discarding a zero pair leaves 2 negative red counters, a fall in the value of the stock. The value of the stock has decreased by 2 points. Again, the context is helpful. The magnitude of the gain over the first 2 days is exceeded by that of the loss on the third day. The overall change is represented by a negative number. This solution can also be modeled using a number line. We invite you to take a moment to make sense of this diagram. We'll take a closer look at number lines in the next problem. Win lives in Surrey. He wants to video call his grandparents who live in Hanoi. What is the time difference between Surrey and Hanoi? Time zones roughly follow longitude and are offset in relation to 0 degrees longitude. Surrey is 8 hours behind this standard time. Its time zone is represented by the integer negative 8. Hanoi, on the other hand, is 7 hours ahead of this standard time. Its time zone is represented by the integer positive 7. To determine the time difference between Surrey and Hanoi, we can subtract the time in Hanoi from the time in Surrey. The time in Surrey, negative 8 hours, can be represented by a point 8 spaces to the left of 0. The time in Hanoi, Positive 7 hours can be represented by a point 7 spaces to the right of 0. The difference between the 2 points can be represented by this arrow. Negative 8 is 15 spaces to the left of positive 7. In context, the time difference between Surrey and Hanoi is negative 15 hours. The sign, negative or positive, is a matter of perspective. Flipping the order gives positive 15. We can say that Surrey is 15 hours behind Hanoi, or alternatively, Hanoi is 15 hours ahead of Surrey. Let's solve one last problem. Applying understanding of integers does not always involve a real-world context. This is true of the following problem. Place the integers and an operation in the boxes to make the equation true. Each integer can be used only once. For example, positive 3 plus positive 6 equals positive 9. How many solutions can you find? Once more, we encourage you to press pause to think and talk about this problem. There are many solutions. Here are just a few. Can you find all of the solutions? How do you know? What strategies could you use? How are some solutions related? We invite you to investigate these questions outside of this video. This video addresses several learning standards in the Math 7 curriculum. In content, we learned about operations with integers, specifically addition and subtraction. Remember that a second video addresses multiplication, division, and order of operations. Your child may be engaged in several curricular competencies in their classroom. Let's highlight a couple that were elicited in this video. Throughout, we explored integer concepts by visualizing counters or number lines. We solved problems both abstract, like making an addition and subtraction equations true from 3s, 6s, and 9s, and contextualized, like determining the change in the value of a stock or the difference between time zones. Engaging in these competencies and more through this content deepens your child's understanding of the following big idea. Computational fluency and flexibility with numbers extends from operations with whole numbers to operations with integers. We hope that you enjoyed this video and found it helpful when supporting your child in their mathematics learning. Remember that there is a second Math 7 Integers video that addresses multiplying and dividing. Please check it out.